8 index laws to review. So before we start on Ex3B, let's see what you remember. Index law number 1, so I'm going to call I1, is what can I please have, Toby?
Was it the, like,
I can set it up for you.
yeah, it's a to the power of m plus n.
Very good. So when you multiply the power, bases that are the same, the powers, you add the powers together. Then index law number 2, I should do this so it looks more like an I. Index law number 2, what is that? Let's go with Andrea.
When you divide the index, it gets subtracted.
That is correct. So a to the power of m minus n. Subtraction matters, so that means m always has to come first, or whatever is at the first one, and the divisor is the second. I number 3, index law number 3. What is index law number 3? Very commonly used. Let's go, Jaden. Ooh, do you want me to set it up for you? Sure. All right. A to the power of m, all to the power of n can be simplified as? Very good. That's index law number 3. So these are the, mainly, for me, I stick to just these 3. I keep it simple. I try not to involve much else, yeah? Unless I really have to. Let's go with index law number 4, which is really just an extension of number 3. Anyone remember? Hands up if you remember. Andrea?
If there's two numbers in there, they both have to the power of.
Very good.
You times the outside power of both of them.
Very good. So index law number 4 is the same thing, except notice there are 2 numbers there rather than just a to the power. It will be b to the power as well. Notice that is times in between, and that means that you do multiply both of the powers, and therefore it should be a to the power of m times p and times b to the power of n times p. Very good. Index law number 5. An extension of pretty much 4 as well, but along with kind of 2, but not really 2. It's more extension of 4. What is that, Raph?
Number 4. Can you set it up?
I will set it up for you. A to the power of m over a to the power of n, all to the power of p is equivalent to?
A to the power of mp over a to the power of np.
Beautiful. So this is saying that you can multiply, even if it's fractional, you'll multiply every single power by the outside power. Rule number 6. Index law number 6. Andrew again. A to the power of 0 is equal to 1. Let's go with the second last one, which you can use in today's exercise. I only recommend it towards the end. What is index law number 7? Let's go with Nishi. Very good. So the reciprocal is then the positive power. And the last one, which most students tend to forget, he wants to give a go with index law number 8. It's the one with the third.
Oh, so like root a to the power of, yeah, that.
What is that equivalent to? This is a one that you don't often use as much. In the next exercise, you probably will. And also next chapter, chapter 4, when we get to surds. Use that a lot more. What's the nth root of a to the power of m equivalent to? Anyone know? Andrea?
A to the power of m over n.
Very good. For those who don't know, as an example in my video, I did say as well that when you say square root of a, okay, this is currently it's a to the power of 1. Even though you don't see a number, because we know it's a square root, technically it's a 2 there. We just don't say 2 because you already know it's a square root. So if you're using this rule, that would be m is currently 1, and then because it's a square root, the denominator should be a to the power of 1 on 2. So it means that if you wanted to do a square root of, 5 on a calculator, and let's say that calculator, if you're doing it on your computer and it doesn't have a square root symbol, so you can't do it, you can actually type in 5 and that hat symbol, that means to the power of, and you can write 1 over 2, that's the same thing. Okay, so if you ever get a problem where you can't find the square root button, you can actually do it to the power of half, and that would mean square root. That also means that if I gave you to the 10th root just means something times itself 10 times to equal a certain value. How can I rewrite that as an index form? It's a to the power of 1 over 10. Very good. So that's key just to know, because that is going to be relevant to next exercise, a bit on today as well, but mainly for the next exercise. Okay, so you got your 8 laws. One of my first questions before we do exercise 3B is, why is this true? Anyone explain to me? Because there's a logic to it. Raf?
You take like 3 squared and 3 power of 1.
Like that?
Yeah.
Yep.
That would be 9 times 3. Which would then be 27. And if you do 3 to the power of 3, that's also 27.
I like how we're doing it by, so to inference, we know that the value of this ends up being the same value as this. Another way that I want you to see, okay, is actually just breaking it apart, because that's literally how you first learned what indices were. Indices is repeated multiplication. Multiplication is repeated addition. Yeah, if you didn't realize that. You did addition in grade 1 and 2, and then after you did addition, you're pretty good at it. They're like, great, since you add a lot, let's learn multiplication. It was a short form of repeated addition. After you learn your times tables, then they're like, great, because we use a lot of times tables. So they say, well, how do we simplify if you keep multiplying something over and over? For example, doubling. For example, cell growth. If something doubles every time it spreads, it doubles the amount of spread it has, then you don't want to be sitting there doing plus, 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 and you don't want to be sitting there doing times, 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 times. So they came up with indices. So when you say here, and Raf said 9, which is correct, but the step between it, I'm going to pull it down. And you can see the logic here. 3 squared means 3 times 3. Then you say times, and you got 1 3. If I asked you, what is that simplified, you don't want to sit there and write 3 times 3 times 3, because that's what we were trying to avoid. We were trying to come up with a new notation that avoids repeated addition, multiplication. It takes too long. We use indices to collect that. So if you have the same basis, and notice it's 3, 3, 3, and it's repeated multiplication, well, then we collect them. We say, well, that's base 3, and I'm multiplying it itself 3 times. But how did I get the 3? There was 2 of these 3s plus an extra 3. That's why we say when you multiply with the same basis, we add the powers, because that just tells me how many 3s I'm going to have, which is over here. So I said I'm going to have 2. I do have 2. Then I said I'm going to have 1. I do have 1. 2 plus 1 gives you 3. Which makes sense. Let's go to number 2 then. So if that logic is true, then why is the subtraction true? Let's think about it. I'm going to do it over here now. If I gave you 3 to the power 5 divided by 3 to the power 3, you would tell me, based on the rule, it is 3 squared. But the logic to this, let's break it apart. 3 to the 5 just means 3 times 3 times 3 times 3 times 3. No one wants to do that. It's too long to write. Divide is actually the same thing as writing over. So I'm going to write it as a fraction so you can see it. 3 cubed just means 3 times 3 times 3. You see what happens? When you divide them, remember with fractions you can split up the multiplication. It could be 3 over 3 times 3 over 3 times 3 over 3. But then what's missing down here? 1, because it's 3 as a fraction is 3 over 1, 3 over 1. If you split up the entire fraction, it actually ends up just being 3 over 3 times 3 over 3 times 3 over 3 times 3 over 1 times 3 over 1, which interestingly, we know what 3 divided by 3 is. It's 1. Which is why we end up saying, well, I had 5 on the top divided by 3 on the bottom. Well, naturally, it's kind of like 5 will lose 3 because they will end up just being 1, 1, 1. So 5 take away 3 gives me 2 left on the top. This is why we say 5, when we write it out, 3 on the numerator, 5 on the numerator minus 3 in the denominator gives me 2 left in the numerator. This is also one of the reasons why number 7 is true. So if you think about rule number 7, what's rule number 7? If I flipped it around, if I said 3 cubed divided by 3 to the power of 5, you can see the logic now. This would be 3 to the power of negative 2, and you guys told me it's the reciprocal. Well, why is that? Same thing. If you actually drew it out, it makes a lot of sense. 3 times 3 times 3, that's 3 cubed. Divided by, you got 5 of them on the bottom. So if you got 5 of them on the bottom, same idea. If you divide them, naturally, 3 divided by 3 is 1, 1, 1. So there's 1 on the top in the numerator. And the denominator, I've got 2 left. That's why it ends up being 1 over 3 squared. But that comes from rule number 2. And rule number 2 just came from fractions. Does that make sense? And if you follow that idea, that's how rule number 6 comes about as well. 3 cubed divided by 3 cubed. That's how we know, or by inference, we know it's 1. And if you then have a guess at rule number 3, I'm not going to show you this, but you can actually figure out rule number 3 using the logic we gave. So if I gave you 3 cubed to the power of 4, why do we times them? What if I rub this off and I said a to the power of 4? What does that mean? That is true, but I just want to know, what's a to the power of 4 the same as? A times A times A times A. That's literally what we know what indices are, right? What if I change that A and then I put 3 cubed? So 3 cubed times 3 cubed times 3 cubed times 3 cubed. Now we know from rule number 1, what do you do to the powers? You add them. But back in primary school, we know that if you do repeated addition, 3 plus 3 plus 3 plus 3 is the same thing as writing, 4 groups of 3. That's why we knew, well, if you did to the power of 4, you end up actually just doing 4 groups of 3. So that's why it's 4 times the 3. That's what you're really doing. Okay, and that's where the logic comes in, that this is just a short form that we learnt, just basing from one simple concept that we're saying anything with an indices just means repeated multiplication. So you can actually go through all 7 laws just by doing that as well. The hardest one to figure out is 8. If you want to have a go, that's in your own time to actually extend yourself to figure out why is rule number 8 true. Okay, so I've shown you 1, 2, 3, 4, 5, 6, 7. You can use everything I just taught you there. I haven't shown you 8. See if you can figure out 8 on your own. But otherwise, let's now start on exercise 3B today. Okay, so I said to you, today's exercise is very similar to what you've been doing in exercise 3A. The only reason why this looks scary is because there's a lot more fractions, negatives. But if you stick to what I say, stick to the first 3 rules, keep it simple, don't try to make it more complicated, and it should be much easier to do. Okay, here. I'm going to do the first one. A. Numbers with numbers, letters with letters. So for those who struggle with their layout and algebra, maybe this could help you. Others, you might already have your own technique. That's fine, yeah? This is what I would have done. I would have split up numbers with numbers, so 3 over 9 times, because that's times in between all of them, I keep all the m's together, and then I keep all the n's together. So what I get is m to the power of negative 3 divided by m to the power of 4 times n to the power of 6 divided by n to the power of negative 2. Let's simplify. 3 over 9 is simplified to what? Can I please have mirror? 1/3, so I keep that as 1/3. Times. This here, you can use rule number 7, but I don't like using fractions within a fraction. So what I do is I just literally do rule number 2. Rule number 2 says if you got same basis, which we do, you got a power, negative 3, and you got a power of 4, but you're dividing. When you divide, you subtract the powers. So here, this is the same thing as you saying m to the power of negative 3, take away 4. Times. Same thing with the next one. All the n's. I'm not going to flip it. I'm not going to change this to a fraction because it then becomes n to the power of 6 divided by 1 on n squared For some of you, that might be intimidating, but I would rather not change it to a fraction. So I just do rule number 2 again. N to the power of 6, take away -2. Let's work it out. 1/3 is still 1/3. -3 minus 4 is -7 times 6 minus the -2, double negative is plus. So 6 plus 2 is 8. That's pretty much the correct answer at the moment. But you never leave your answers with a negative power. Okay, by the time you get to year 12, if you leave your answers with negative power, they penalize you. Okay, at year 9, I keep reminding you. And then year 10, I might penalize you. And then year 11, I definitely penalize you. Okay, so here, never leave your answers with negative powers. They just don't like it for some reason. It's just the way they mark it. So here, make sure to change that to a positive power. That's when you use rule number 7. See how I'm doing it? I don't do it within the calculations. I do it at the end. So here, this is the same thing as saying 1/3 times 1 over m to the power of 7. That's rule number 7. Times n to the power of 8. Well, currently it's not a fraction, so I'll write it as a fraction. Over 1. Final answer should be, numerator is all calculated as 1 times 1 times n8. 3m7. Now, I know I took a lot of steps there, but can you see the way I'm thinking? I usually do the first 3 steps in my head, and I write this line, and then I write the answer. So I usually only take 2 steps there, but I'm breaking it apart so you can see how my mind works. I go through numbers with numbers, letters with letters, and if you stick it to that way, it's very organized and you can work through the problems, no matter how big. Yeah? Let's try the next one. Here we go. Get rid of all the brackets first. This is where rule number 3, rule number 4, rule number 5 is good. Break it all apart. 3 times the powers and then -1 times the powers. So you should have p -3 q3 all over 2p -2 q² divided by p +2 and q -2. Okay, so I get rid of all the brackets. From here, I like multiplication. I don't like division. What do you do when you divide fractions again? What do you have to do? Jaden. All right, maybe Sean. The reciprocal. So next line is when we're doing multiplication, we change it to times. This now becomes q -2 over p². This is p -3 q3. This is 2p -2 q². See how I'm keeping it very clean? And then from here, like I said to you, I would do numbers with numbers, letters with letters, so all the p's, all the q's, and all the numbers together. Now, I usually do this in my head, but I'm going to write it out for you to see in what's happening in my mind, okay? So this is what I'm doing in my mind. I see the 2 on the bottom. So that means there must be a 1 on the top. That's the only way because there's a coefficient of 1 here. We just don't write it. So I see a half times, I write all the p's together in my mind. I say it's -3, p -2. No more p's. Now look at the q's. Q in the top is q3 times q -2 divided by q². I'll show you. I just forgot there's a p² over here too. Okay, so p -2 times p². That's on the bottom. P -3 is on the top. There's a q3 times q -2 on the top. And there's 1 q² on the bottom. See how I'm keeping all the letters together? And from here, I literally still stick to rule number 1, number 2, and that solves the problem. This just means add the powers on the bottom, so -2 plus 2, we know that's going to be 0, so that ends up being a 1 on the bottom there. P to the power of 0 is 1, and you have the top is p -3. Now I would do that in my mind. I'm just sort of showing you what I would have done. Okay, so from here, half times, this is p -3. Notice the bottom is going to be p0 times, to the top, add the powers. 3 plus -2 is 1, and then you're dividing by 2. Usually I do it all in one step. This is what I would have done. So usually I would write it as p -3 divide, means you subtract the powers, and here just got to be careful because they come together. I would use the brackets there. That's negative 2 plus 2. The reason why I wrote it as a fraction before so that you didn't make that mistake. So if your layout is poor, you'll make a mistake here. Okay, so that layout is key. If you don't want to skip steps, or if you're not good at these errors here, then do the steps I did before. But this is how I normally do it. So I would collect them all together in one step. Same thing with the next one. I would write it as Q 3 plus a negative 2, take away 2. Can you see what I'm doing there? I'm just following index laws. Add the powers, so 3 plus negative 2. Take away, because I'm dividing, take away 2. If you do all of that in one step there, you should get half times negative 3, take away. Now that's 0, so it's just negative 3 here, so P negative 3 times Q. 3 take away 2 is 1. 1 take away 2 is negative 1. Okay? And just showing you sort of the thinking that I'm doing there. So you can use whatever method you like. That's just key there so that you understand how I do it. I find it easiest if you keep it simple. Don't try to flip things around. If you do that, you may be more prone to mistakes because fractions and negatives are one of the biggest challenges for students, especially when it comes to layout. So I stick to 1 and 2. Okay? Answering the question, P negative 3 and Q negative 1 is the same thing as saying, whoops, half times 1 on P cubed times 1 on Q to the power of 1. So really your answer is 1 over 2P cubed Q. Okay? And that's pretty much what you'll be doing today's lesson. All of these problems here follow for the fluency section. That's as problematic as you could get. They can probably chuck in a couple more numbers in there, but otherwise, that's how I would do it. You find your way, what works for you, but I find sticking to the basic rules, 1 and 2, you'll be able to do most of the problems here. Now, the next 2 questions, enrichment. If you watch my previous video, you probably have an idea of how to solve this one. I haven't taught you the inverse of exponentials. It's called logarithms, which we will learn in this chapter. But that means to solve these problems, you can only do it by comparison. What is solving by comparison? Let's have a look at these 2 examples. Solving by comparison is something like this. If I gave you 3 plus something is equal to 3 plus 7, what's that something? 7. You did that by inspection. What you didn't do is you didn't use algebra and say 3 plus x equals to 3 plus 7, which is 10. You didn't say subtract 3 on both sides, and that gives you 7. That's very likely the technique that you didn't do because you know inverses, right? What you likely would have done is you didn't use inverse operation, but instead you did observation. You looked at that by inspection. You said, well, since they're both equal, they both have a 3, they both have a plus, well, what if they're adding? These 2 must be equal, right? So therefore, if this is 7, this must be 7, right? So that's what we do to solve these problems. Same idea, if you can replicate the equation that the left looks exactly like the right, then you can say whatever x is, which is the power, must equal to whatever the other power is. Right now, that's a fraction. That's a base 2. I need this to be not a fraction, and I need it to be a base 2. So let's break it apart. 32. Is there a way to write 32 with a base 2?
Yes.
2 to the power of what?
4, 8, 16, 32, 5.
5. Very good. So this is the same thing as writing 1 over 2 to the power of 5. But they were so similar. They're so close. This has a base 2, has a base 2. One is a fraction, one's not. There's one rule that we can use that changes it up. Very good. Rule number 7. You can bring this one up to become 2 to the power of negative 5. Rule number 7 is if it's negative, you do the reciprocal and it's positive. So by doing the reciprocal again, brings it back up. Now the bases are the same. By just inference, by observation, the powers must be the same. See, 2 to the power of something is equal to 2 to the power of something. So that means x must be negative 5. So this is called solving by inspection. Okay? You're essentially just by comparing it. Same thing with the next one. You got 2 over 3x to the power of x. Same concept. What can we do to the 9 to get that 2 on 3? That's tricky, isn't it? Beautiful. So let's start there. So we've got 2 over 3 to the power of x is equal to 3 squared, 2 squared. Now we've got the 2. We've got the 2. We've got the 3. Few problems here. It's not 2 on the top and 3 is not on the bottom, but also I don't need this 2 squares. What do? You can make it a power of -2. Now, there's a couple 2 steps here actually. This 2 over 3 to the power of x, you can say, because it's squared, remember rule number 4, if that one's squared and that's one squared, you can use rule number 5, the fraction one. You can actually write it as 3 over 2 all squared. True? Because it's 2 times the power of 1, and then 2 times the power of 1 will give you that. But then, we're just slightly off here. That 3 over 2, which is what Nishi was trying to say, we need them to be flipped. The only way it was going to be flipped was if this was a power of -1, and that was a power of -1. True? So if this was a -2 and that was a -2, then that means that would become the reciprocal, then flips down to 3, and then the 2, the reciprocal goes up to the top. So this is a bit of a tricky, there's 2 parts there, rule number 5 and rule number 7 together. So what am I saying? I'm saying this is the same thing as writing 2 over 3 to the power of -2, because if you times it, 2 to the power of -2 becomes 2 squared, true? On the bottom. And then this is 3 to the power of -2, which is the same thing as saying 3 squared on the top. See what I'm doing there? So those who are confused, I'm going to write it again, just so you can see it. What I'm saying is this is the same thing as saying 2 to the power of -2, and this is 3 to the power of -2. You see that? The 3 squared, if we're using rule number 7, can be written as 1 over 3 -2. 2 squared can be written as 2 to the power of -2. The reciprocal goes back up. But they're both rule number 5 says you can rewrite this as 2 over 3 all to the power of -2. Does that make sense? So if it helps you, think of it this way. Follow the arrow. That helps you to see it. Okay? And therefore, they both now have 2 on 3s. Both 2 on 3, which is great. That means the powers must be the same. X equals -2. Okay, so I'm going to zoom out. This one was a tricky one with that 3 squared. So you can flip the numerator to denominator by putting a negative power. And we knew it was squared because, like Una said, changing a 9 to a square is just how you then flip it around. Okay? But that's an enrichment type question. So that gets you to problem solve. Think about rule number 7. Okay, so that's exercise 3B is working on rule number 7. All right, team. It is now 9:33. You've got about 40 minutes of your time to either work on 3A if you haven't done 3A from our last session, or you can work on 3B for today's session.